We want to talk now about examples of homogeneous differential equations which have variable coefficients. We want to begin by first introducing some terminology. So we can write a general equation, second order homogeneous differential equation with variable coefficients in this form, with the coefficient in front of the second derivative term defined as the function p of x. Q of x is a function multiplying the first derivative term. R of x is yet another arbitrary function multiplying the dependent variable y. And so the sum here on the left hand side is equal to 0 is the differential equation. And let's say it's defined over some interval in x, which we're denoting I, and that's defined with x ranging between the values a and b. All right. So we're going to assume that the functions capital P, capital Q, and capital R that appear in the differential equation are analytic functions on I. So practically speaking, what analytic functions means is that we can evaluate derivatives. These functions are continuous and we can differentiate them as many times as we need, and everything will be fine. They will not blow up any place. That's what is meant by analytic function in a practical sense. Mathematically, we can define this later. And we'll also assume that these functions do not have a common zero. That is, there is no place within this interval where all of these functions simultaneously vanish. They would not vanish all at the same place. They can vanish in one place. Function p can vanish in some place. Q can vanish in another place. But p, q, and r all together don't vanish at the same place. So an example of functions which satisfy these properties would be functions p, q, and r which are polynomials in the independent variable x. So if they are polynomials, we can factor them with respect to the zeros they have, and so the assumption is that they have no common factors, and so they will not vanish together at any place within this interval. All right? Okay, so given this, we can define the terminology of what is called an ordinary point and what is called a singular point. Now a point x equals x0 is called an ordinary point if this coefficient of the highest derivative term, p, capital P, at the point x0 does not vanish. If it does not vanish, then the equation in some sense, qualitatively speaking, is very well behaved, is very smooth, and so on. And so the point x equal to x0 is called an ordinary point. And so this is to be contrasted with the situation where the function p of x naught does vanish. So when it does vanish, then some interesting things happen. And so these points, in fact, one can show control the behavior of the overall function, and so we can call them extraordinary points. They exert a lot of control over the behavior of the function, and they are mathematically called singular points. So the mathematical terminology is that points where p of x naught vanishes is a singular point of the differential equation. And so it's this terminology that we're going to be using just as we proceed. So let's use this terminology to establish some very simple observations. So suppose this function p of x is not equal to 0, we can divide the equation by it, and then we have this equation with the simpler representation y double dot plus p of x, little p of x times y prime plus little q of x times y equal to 0, where the lowercase functions p and q are basically the big Q divided by big P and big R divided by big P again. And so it's in this form that we had previously used the equation and had discussed the existence and uniqueness result and so on, and we wanted to define the equation more generally, but to remind you of the existence and uniqueness result for initial value problem for equation written in this form is that this initial value problem has a unique solution. We are just reminding you of the initial value problem. It has the initial value of the function y at point x naught being given as y naught, some arbitrary value y naught, and the slope of the function y at position x0 is also given as some arbitrary number. Both y0 and y0 prime are some arbitrary numbers. Given these two initial conditions, the theorem says that there exists a unique solution provided that the location where we are prescribing these initial conditions is an ordinary point. So provided we specify initial conditions at an ordinary point, we can solve the differential equation under the assumption that P and Q are continuous functions over the interval that we are dealing with the problem. And so this is what we have been discussing previously. And another way to state this result would be that if x0 is not an ordinary point, if it is an extraordinary point or a singular point, then we cannot have this freedom that we previously had. We cannot pose arbitrary initial conditions. We have to look at the nature of the solution close to the singular point, and that will constrain the choices that we have in order to have a solution.